My pleasure to introduce today's seminar speaker, Qianyao C. She is a grad student in my lab working on her PhD. She got her BS in forestry from Shandong Agricultural University in China, and did a master's in environmental science at the University of Florida on nutrient cycling and green infrastructure. And here she's been working on stormwater from a more systematic perspective, as you can see from her title. She's been collaborating with faculty and students and postdocs in civil engineering, urban planning, and public health while she's done this work. And she's won a couple of awards for the work that she's done. Just to name a couple of the long list, she was a UMD Global Stewards Fellow from their Research Traineeship Program, and she won both a Summer Research Fellowship and Wiley Dissertation Fellowship from the grad school. So,
Thank
take
you.
it away. Yep.
Sure. All right, check. Thanks for the introduction, Mitch, and welcome everyone for my Access seminar. And today I'm excited to share the work that I've been doing a couple of years on developing the digital twin framework towards the urban adaptive management for stormwater. So let's get started. Set up the background first. Like nowadays, in more and more areas, including our campus, stormwater is becoming harder to manage as there's increasing challenges and uncertainties from climate extremes and also the land cover change. So on the one hand, due to climate change, we are seeing more intense and also more frequent extreme rainfall events, and also the exploding urbanization, urban sprawling has converted most of the surface, like natural surface land, to impervious coverage, impeding natural infiltration and thus converting more and more precipitation into stormwater, surface runoff. And this in turn will bring like real and also negative impacts to our life, such like water quality concerns as the stormwater collects and carries the pollutants, the contaminants along its pathway and will be discharged to the natural water bodies. And also as people living in city, we are more prone to interact with the flooding, with the like already impaired water bodies, which bring public safety and also a health hazard. Furthermore, the traditional way of management stormwater is always like a one-directional process. Once there's hazard occurred, people make reactive respondings like maintenance or retrofitting or sometimes even rescue. But it's always considered reactive or passive without sufficient resilience to mitigate the hazard or like cope with the risk ahead of time in an adaptive way. So in this case, to address, the adaptive management concept has been gaining more and more attention. Instead of linearly react to the hazard, it underscores the concept of the iterative learning process, starting from like measurement or like assessing the situations, taking the measures to continuously learning and make adjustments. And to really spin this cycle, it really relies on a continuous information updating and sharing throughout the stages, and where a connection between physical states and the virtual platforms for analytics is called for. And to do so, one possible way is to build the stormwater digital twin. And what is that? What the digital twin is? So it's like a live replicate, a virtual replicate for the real world, built by dynamic data and digital information collected from the physical entities and hosted on the virtual cloud layers. So as the physical conditions change and updating, their corresponding digital twin could keep up with fast varying conditions and let servers like us to test out what may happen next. So a vivid example here for the digital twin applications is the driverless car in the transportation field. So these vehicles constantly sensing their surroundings and turning the physical traffic patterns into data and then digitally communicating with the virtual navigation model to make very quick turnaround times of the driving decisions. And the stormwater system in cities need the same levels of intelligent care, but currently it still lack of full attention in both research and also in practice. So in my case, I would like to see if we can migrate some of the explorations of digital twin framework from other field to stormwater management. So let's see what we can learn from the development of driverless car, like the autonomous vehicles. Those cars don't drive themselves randomly. The whole process of the driving decisions relies on three fundamental pillars. Firstly, a detailed roadmap. Secondly, the sensors to perceive real-time surrounding traffics. And lastly, a virtual platforms merging the spatial and observation, like sensor data to build navigation models for informing driving decisions. So mapping, monitoring, and modeling, we could extend the same principles, and they can be the same foundations that we need towards the stormwater digital system. So correspondingly, in our stormwater realm, we need a holistic grasp of the drainage network maps, stormwater flow monitoring continuously, and similarly, we have our hydrologic and hydraulic models for simulation and sometimes even prediction. So from here, I'm gonna show you the journey that how I approach the digital system of our campus, stormwater, following these 4 M's as backbone. So we started with mapping, aiming to understand and define, say, at the outfall scale, where stormwater comes from across campus, and using spatial and drainage infrastructure information. And then comes to monitoring, where we set up the sensor system to at the outfall again to continuously or at a very fine temporal resolution to capture the stormwater behavior, and also build the virtual platforms for such data processing, analyzing, or like visualization. And based on both mapping and monitoring observational inputs, we move forward to the modeling phase, aiming for answer questions like about input sensitivities, and also develop the ground truth calibrated local models to predict runoff under different scenarios. And then finally, all the insights would be grouped together for the final management, where all these insights gather together to support a more resilient or adaptive stormwater management strategies. So let's begin with the mapping study. But firstly, I would like to get 2 fundamental concepts clarified: watershed versus sewershed. So a watershed should be very common for us, like it's the contributing areas of land where all the surface water is gonna drain to a common locations, normally like a stream or a creek, and the area is defined by the topography, like the natural topography, following very simple principles, gravity, right? Water flows downhill. But it's not always the case. If we zoom into the city system, or even a finer scale, where we have man-made drainage infrastructure that alters the surface water flow patterns, and that's where sewershed, this concept, got onto the stage, and specifically for us, that would be stormwater sewershed. And if we still stick to the way we define watershed boundary to sewershed, we will definitely miss all the details about like how drainage infrastructure impacts the surface water flow. So that would be definitely not accurate. Taking our campus as an example, so yeah, this map shown here, it's the sub-watershed of part of our campus, determined only by topography. So DEM here is short for Digital Elevation Model, which contains high-resolution surface elevation information as a raster. And from this figure now, we couldn't really tell any drainage information, especially the points that I highlighted here. It's some key outfalls of our campus, but for here, like it seems just random points within the boundary without any information how it interact or related to the surface water. But actually, in reality, this type of drainage infrastructure feature is really a key intersection where the stormwater collected by the pipeline meets the natural water body. And in our case, that's the Penn Branch Creek. That's where the pipeline stormwater being discharged to these natural creeks. And for the targeted stormwater management, for sure, like the sewer shed determination at such outfall scale would be the very fundamental information. And to give you a sense, like this is the sewer shed that we delineated with the consideration of drainage infrastructure. And you can see how different they are with and without the considerations of drainage infrastructure. But how the way we define watershed has, So the process of watershed delineation has been already widely and commonly applied, but there's no a standard mapping method for sewer shed. And instead, in practice, this type of determination, the sewer shed determination, is still heavily manual. Like it's basically depend on the visual inspections or like based on very local engineers' expertise or knowledge. So that's the kind of motivated me to explore mapping method that is infrastructure informed and also to identify specifically, realistically, which area of campus drains stormwater to specific outfalls. So in our case, throughout this study, we focused on 3 key outfalls of campus as the study subject. So here's the quick overview of how I shift from catchment to sewer shed. So started with data collection for sure, gathering and pre-processing spatial data like DEM surface elevation rasters, and also the detailed drainage feature distribution across campus. And then we tested 3 mapping methods in the GIS context, which I will break down in more detail in the next slides. And lastly, for sure, we conducted a series of validation to test accuracy and also the comparison test to check the consistency among 3 mapping results. A closer look at the mapping approach we tested. Well, the first one I listed here is just for reference because that's what I manually draw up. So I manually wrote the runoff towards the surface drainage features, treating them like inlets or the manholes, treating them as the entrance point where stormwater starts getting into the pipeline system. And next, I used using GIS to do some tricks on the elevation raster to better reflect the influence from the drainage. So firstly, in ArcGIS AJ1 approach, we lower the elevation values on DM at the locations where we have inlet or manholes. Consider that it's like digging a virtual depressions on the DM layer, so to mimic how in reality these features capture the surface stormwater. And then comes to the second approach is where we applied another assumptions, forget about the surface features like manholes or inlets, but we consider the whole underground pipeline system as a virtual but functional streams, and then we bury that onto the DM, lower the values of these pipeline locations. So in this way, the water will be drawn into such pseudo channels, redefining the flow pattern. The third one is logically similar to the first AJ1 approach, but was more semi-automated, and that was deployed on QGIS platform. So conceptually, inlet and manholes are still considered as depressions to guide flow, but unlike in ArcGIS, where we manually twisted the DM values, QGIS has their own generic tools that they can automatically consider the inlet or manholes as the depression, so long as we insert that command. So on the one hand, QGIS has limited flexibilities for us to adjust the DM rasters, but on the other hand, it's more scalable for broader applications. But anyway, different tricks and principles. Now that we laid the drainage infrastructure impact onto the DM, the following process of delineation, catchment delineation, just follow the basic steps, starting with identifying the flow directions, accumulation locations, and finally by grouping the related sub catchments into a complete data catchment shapefile for the specific outfalls that we are looking at. Of course, validation is essential, and we here randomly selected location points within the resulting boundaries to compare the mapping predicted water flow directions versus what we observe on site. So all three mapping methods achieved satisfying results in this phase, with AJ1 method outperforming by just a little bit. And when we further sorted the observation points to the land cover types, we still saw strong consistency and high agreement across varied surface types. And further, we would like to assess how replicable these mapping methods are. Here we started from the qualitative analysis, qualitative comparison, say compare the graphical outputs of the catchments. Where, we firstly compare the basics of the resulting shapefile graphs by looking at the area size, the parameter length using geospatial fragment test. And here we got no significant differences being detected. And further, we use the dice similarity coefficient to measure the spatial overlap between shapefiles. So the results here returned good reproducibilities across method pairs. So altogether, this comparison, graphical comparison, preliminarily support the consistency across mapping methods that we explored. And further, we would like our comparison or result to be more robust or more scientific sound. So we conducted the quantitative comparisons, but with the use of hydrologic models, simulations. So we'll touch base on more details about that in our modeling phase, but not for now. But even so far, with careful delineation, validation, and part of the comparison, we should have a bunch of confidence to determine, say, at the specific outfalls, where the stormwater is coming from across campus. And the next step is to understand how it behaves and bring us to our next phase, the monitoring. So on campus, we built the Internet of Things Living Lab concept to do just that. We installed the IoT sensor network at 3 out of the 3 studies outfall sites, and this is one example to show the model, the sensor setup. So on site, we have what we call Sondi sensor containing multiple probes to detect the water quality parameters. In our case, we have pH values, oxygen levels, and turbidity and conductivity being measured on site using this sensor. And at the bottom edge of the pipe, we installed the Doppler meter, which used the ultrasound to actively detect the water depths, velocities, and then converted them into water flow rate, which we consider as the indicator of water quantity. And lastly, we have the data logger on site. On the one hand, it supplies the powers to wake up the sensors every 5 to 6 minutes for one measurement. And on the other hand, it stores and transmits the data from the sensor to the cloud and to the server almost simultaneously. And getting onto the cloud, we have tried and utilized commercial platforms such like AWS from Amazon or Google Cloud GCP from Google. They all have the functionalities to stream and also update such big data in a very quick turnaround time and efficiently, robustly. And they also grant functionalities for users like us to further clean our raw data process and get visualization. So next step, this page, I've introduced most of the basics of this system already, but the main thing that I want to highlight here is we built the public-facing data dashboard where we aggregate all these big data into an accessible way where the public could interact with this type of data with their own interest. For example, they could select parameters at any of the outfall sites, and by toggling the time frame bar, they could get either a holistic view of the stormwater behavior or trajectory over time, or they can zoom in to a very specific time period, say when there's rainfall. That's the snapshot from a very single rainstorm period, and we can see the hydrologic signatures in a very fine, like every 5 minutes time resolution, making sure that we are not missing any details about how the runoff being responding to the rainfall events. So altogether, this living lab bridges both broad scale monitoring and also the fine grain hydrologic insight onto the same page, setting the strong empirical data for further modeling calibration use. And together with the prior mapping results, we are ready to get onto the modeling phase to test out the localized runoff simulation. And again, workflow. We use the PC-SWIM stormwater management model developed by EPA to test as the platform to learn about the virtual stormwater simulation. And this workflow seems a little bit complex at the first glance, but it can be really streamlined to two major pathways. So firstly, remember that we left a tail in the mapping study that about quantitative comparison. So this is where we answer that questions. We here use the hydro simulation output to quantify the impacts varied mapping techniques may bring to the simulated runoff behaviors, and we apply further statistical to formally test the consistency across the mapping method. And then come to the traditional model development step, with feeding our IoT data from the monitoring phase as the ground truth, and also the varied rainfall scenarios to embrace climate uncertainty. But start with basic model setup. So you are looking at the software of PC-SWIM, the interface, which we embedded with multiple empirical hydrologic equations, models, and this is where we input all the necessary data to set the model up. So spatially, we have to firstly define the outfall of our interest, the pipeline system connected to it, and of course, its contributing area that we acquired from the mapping studies. And on the right-hand side, you can see there are so many spatial parameters for later our calibration use for define the stormwater behavior. And temporally speaking, at this stage, the temporal input is gonna be the rainfall record. And to pair up with the time resolutions of our ground truth runoff data from the IoT, we here use crowdsourcing a precipitation record from the local rain gauges as the time series input. So loading both temporal and spatial information onto the model, we could get a simulated hydro response in just one click. And again, we use the flow rate, runoff flow rate as the indicators for the overall behavior. In getting to the first chunk, the model outcome comparison. So we input varied catchment boundaries acquired from each AJ1, AJ2 QGIS mapping techniques into the simulation, while keeping all other parameters still and uncalibrated. So showing this simulation hydrographs, visually, this runoff curves overlaps almost perfectly in terms of the trajectory. We did see some variations in terms of the runoff flow rate, especially during the peak flows. But whether it's significant or like influential enough, we need statistical support. So we firstly applied the generalized linear mixed model to test that. So in addition to the mapping method, we also consider the rainfall size, rainfall intensity as another fixed effect into this statistical model, which So it's a known driver of the runoff behavior already. And we categorize them as 3 levels, heavy, medium, and light. And given we had 15 rainfall events in total for testing, and 5 per each rainfall category. The figure shows very clearly that the rainfall size consistently showed significant effect on the simulation, on the runoff behaviors, which is expected. But we don't have any significant effect being detected based from different mapping inputs, which let us get to the statement that there's no significance in differences as for now from the mapping techniques that we applied. But that alone doesn't necessarily imply that we got interchangeable mapping methods for catchment delineation, sewer shed delineation, because in practice, even small variation in simulation may still have their own implications for management, and we don't want to miss that. So we went a step further from testing differences to testing equivalence. And we applied TOST, two one-sided test. You can think of that as double reverse t-test rather than traditionally t-test. They compare whether 2 datasets are different. TOST checks whether 2 datasets are similar enough within a predefined practice difference, like a difference boundary. So in our case, we set the margin of that difference bound to 5% of the peak flow for each testing scenario. And I also wanted to highlight that this margin is set being highly conservative, and as a reference in the medical field where the TOST, this equivalent has been mostly used, probably to test their effect from different treatments, they normally set this practical difference margin to 20% of overall variation. But since we want to embrace, we don't want to miss any impacts coming from our very initial fundamental sewer shed techniques, we set this margin to 5%. But even being conservative, we still got strong results. So for example, all mapping comparisons under heavy and medium rainfall input, they all pass the equivalence test across all the study sites. And 2 out of 3 catchments, all for 3 and 5, they returned equivalent results regardless the rainfall input. It seems like the only variation comes at alpha 19 during the light rainfall input conditions. But we can explain, it's not a surprise to us because light rainfall for sure will generate small volumes of the runoff, and plus that 5% of the threshold that we apply to determine the equivalence, even teeny tiny simulation variation may still be magnified and then fail the equivalent test. And also, if you look at the map, you can easily tell that alpha 19 has the smallest contributing area other than the other 2. And I can also tell you that the imperviousness coverage for alpha 19 is the smallest, like it's more dominated by the pervious undeveloped areas. So naturally, this region will return much smaller volumes of runoff, even under same rainfall situation. So all in all, the equivalence was mostly supported by the results, and further and finally supported us to confirm that we got interchangeable mapping methods that can across varied storm conditions, and the varied sewer shed mapping techniques will produce comparative and even equivalent runoff simulation results. That help us to conclude the first stage, but also help us to streamline the subsequent modeling steps, because we could therefore adopt just one representative catchment input as a spatial configurations rather than repeatedly testing different scenarios. And for the model development, we started with sensitivity check because if you can recall, there's a long list of the parameters that may be contributing to the final output. So we wanted to know which specific parameters that influence the simulation most before exhausting time and efforts to fine-tune each of the parameters in the calibration phase. So here we apply the one at a time approach, tested throughout 4 rainfall conditions to try to capture all the variance that precipitation may bring. And we see commons and differences from the results. So what in commons are the impervious coverage of the contributing area dominated in the runoff shaping across all the scenario, and we see flow width appear as the key factor consistently as well. And the differences came interestingly, but also reasonably. Like under the light rainfall conditions, the runoff, the model seems more sensitive to the impervious surface feature, like the roughness of the impervious or their connections or the storage, the depression storage. But if we get heavier rainfall, the features of pervious surface like soil or green space, they might, it's more influential to the overall simulation results, especially the parameters that directly related to the infiltration process, like the suction head or the hydraulic conductivities. So in all, we embrace all the variations and consider all 8 parameters here at the sensitivity parameter for calibration, which still seems a lot, but luckily we have a function in PC Swim called radio tuning calibration, which is very helpful for us to adjust the parameters quickly and also strategically optimize the fit between what's being modeled and what's being observed. So we have 6 rainfall events for calibration and 4 for validation, which selected again to represent a wide spectrum of the rainfall characteristics. And for the performance evaluation, we introduced matrix like NSE, R square, and also the root mean square error as the indicators. Just zooming into one example from the calibration phase, this hydrographs show how the simulation being improved over time. Like the right line, it's the time series runoff data that we acquire from the IoT sensors, which serves as, again, as ground truth. And the blue line is the very initial uncalibrated runoff model output. And in between, you can see the iterations of parameter adjustment to make it align better. And that's another example of calibrating. Note that the calibration process, the target of the calibration was never go perfection, but to ensure the reliabilities or the consistency across different rainfall events or like across areas. And that in turn needs like a series or an iteration of the modeling improvement. So if we cannot see the improvement on the hydrographs, we have our performance index matrix to support as well. Validation phase, the final phase. So without further fine-tuning or manipulating the parameters, current settings of calibrated model has already returned solid performance. Here's again another intense examples from the validation, and I think that's under a heavy rainfall scenario, which we have all the index fall within the satisfied range of the the models. And the low flow cases are usually tougher to match because we have relatively small runoff flow baseline and also the noisier data that we may have from the site. But even here, like it's in a very small rainfall event, the model performs quite well. So altogether, this table brings the full performance matrix across all phases, all study sites. The takeaway message here is that we achieved a general good model fit, even though with certain variations for sure, especially under at outfall 19, which is the smallest contributing area we explained earlier. But generally speaking, we got good fits throughout phases, and especially during the phenomenon rain input and also the impervious dominated area, catchment area. So to wrap up the modeling phase, firstly, we confirmed that the choice of catchment mapping techniques didn't really make big differences, which helped the planners, give the planners some welcome flexibility to choose the mapping techniques based on their available data or tools. And also the calibrated swim models performed overly well, especially under the conditions where we may have higher possibilities for flooding. And lastly, if we look at the whole process, essentially, it actually tested out the feasibility of such mapping, monitoring, modeling approach, and also potentially being involved into a predictive tool, not only understand the runoff passively, but also to predict, anticipate, and manage it proactively. So that leads us to our final M, management. So along the way of building such digital stormwater system, we know where stormwater comes from, originated, how it flows, and we use this data set for simulation and to anticipate what stormwater might do next. But to really close this, beyond piling up these information layers, what makes this digital twin really being spinning is to close the loop by using these insights altogether to respond and adapt stormwater risks. So during our project development, we have briefly touched base on utilizing such digital system to inform management, for example, including campus MS4 compliance and pilot reporting, and also with the interactive data dashboard, ArcGIS story map. We have advertised and shared the stories of our campus stormwater with a broad range of stakeholders and audience, which make it easier to later bring them onto the conversations of the decision-making of stormwater management. And also there's definitely a lot more to do. For example, by feeding, say, near real-time weather forecast to the local stormwater models, we can plan ahead for any like flooding issues, or linking the actuators like the valves or gates onto the infrastructure. We could make some automated discharge decisions with the simulation or model insights. So the last chapter of my dissertation serves as a forward perspective, proposing how this digital system can be involved and potentially close the loop of the automation or the learning process. And also a step further, this framework that I presented, will for sure not stop here, but to extend to a multiple scale. Spatially speaking, we can extend it across different across cities, across districts, to test how it performs under different urban layouts or under different climate conditions. And that also means to connect with more elements in city system, like building a communication bridge in between stormwater and, say, traffic models. So we could have some like predictive functionality, the capability to inform the traffic patterns. And also lastly, if we consider the city system as a complex system, we're not only embedded with natural environment, but also the social part, a well-equipped digital twin for stormwater should not go without dynamic social perspectives or attitudes how people perceive or like stormwater or its management. So also in another chapter of my dissertation, I try to develop the cross-sourcing data set from social media mining and this corresponding analysis to incorporate the social perspective into the digital twin of the stormwater, which I'm not presenting here, but definitely will be covered in my defense presentation. And lastly, quite on time, I want to take a moment to say thank you, to shout out to all the support, the insights, and also the valuable suggestions, feedback that's coming from so many along the way. Thank you, everyone, and I'm ready for any questions. Yeah.
Yeah, really interesting. I guess I have two questions. The first is, I'm curious about the flow rates within the pipes versus like open water. And so are they monitored? I mean, is there gauges on each of, like, how much of that is controlled, I guess, versus is it just open flow?
It's not open flow because the sensor that we installed is at the edge of the pipe. So it's definitely not open flow. It's very hard to measure for that. So we are comparing, we are monitoring it's the flow that coming from the pipe.
The flow coming out, not going in.
Not going in, coming.
Out.
Yeah, that's the whole thing.
Okay, all right. Okay.
Yeah.
And then the second question was sort of on the end piece of this about the adaptability and thinking about campus and the fact that we're always building and always changing campus. And so how much, time and effort does it take to sort of like continue to adapt like this digital twin in what is really a rapidly changing, like,
Yeah.
a rapidly changing area, which I mean is the case in most urban environments. Like,
Yeah,
maybe
that's
not as much on campus as on campus, but yeah.
Yeah, it's on campus. It's a small scale for the pilot study. So that's very a good point pointing out that. And also like this, the whole concept of the digital twin is to make it kind of real time updating with how fast the physical world is changing. So for sure, like the monitoring data, it's capturing what is happening now. So it can be a very direct indicators on this part. But in terms of the landscape changing, that's really something that we need to go forward and apply some like updating or automation on the mapping phase.
Yeah.
To kind of set a threshold, like how much variations that we want to embrace, or like after that threshold, we need more insights, like we need more effort to reshape the catchment building. So I guess we don't have that function or capacities for now, but can be a good direction for that.
So really quick, there's some comments on Zoom that I'd like to throw out since they're up there. First of all, Dr. Molinek says, proud of all your hard work, exclamation point, exclamation point. Dr. Shiramahadi says, great presentation. I'm wondering about the cost of monitoring using sensors and IoT at each station, exclamation point. Okay, but he has a question here. So although your model simulations and hydrographs were agreeable, are there any uncertainties that may be involved in the monitoring, the mapping, and modeling components of the whole approach?
Oh, yeah. Let me answer the first easy question about the price. So that's also a balancing point that we need to achieve. Because for now, since we only have 3 sites to monitor, we use commercial sensors. And also of that, like data piling up on cloud, it's based on, it's with the collaborations with commercial. So the sensor itself pretty costly, but we also wanted to, but on the other hand, it ensures the quality of the data because they have a series of calibration, validation before coming out to the market. So we could for sure have more strong confidence on the data quality that we collected. That's a good thing, but also like because of the price, we also it's always our consideration to find the alternative sensors. And I also see a lot of projects that using homemade or lab-made sensors. which is much cheaper and can be applied scalable, but it's like the Q and QC process would be a nightmare if we have this locally, like lab-based. And in terms of the uncertainties, for sure, like because especially during the process of mapping about the modeling, we have a lot of assumptions that's being applied. So all these assumptions can be considered as uncertainty source. And especially for example, during the mapping and also the modeling phase, we consider all the surface water not flow openly, but getting into the pipeline system. So that can be some considerations that can be improved. And also like so many other uncertainties, like the final, that's the one, like green infrastructure, like there are many best management practices on campus, but for the model itself, it contains the consideration of green infrastructure, but there's no way for calibrating it. We can input, or we can choose inputting them or not considering it. But within, it's just no way to test or calibrate anything that's within the green infrastructure, that little piece, but consider it as the open or green spaces. Yeah, that's one part. I can go very broad, but
Thank you.
So is the elevation data the only input for mapping the drainage networks?
in terms of the elevation, yes. But for the watershed process, like mapping process, we applied both surface elevation and the drainage distribution data.
Yeah, actually, to me, like for a very flat landscape, like Maryland, also like the Delmarva area, because it's pretty flat. I think like even we use very high resolution LiDAR data, there are still lots of challenges like mapping the drainage networks. Yes, actually, I wonder how accurate those GIS algorithms are, and how they could like capture the flow direction. I mean, because it's pretty flat.
Yeah, it's nuanced. It's generally flat, but we still see, because of the developments like buildings, like bridges, we still need very high like resolutions to determine.
What's the resolution you use?
Now it's 1 foot resolution. So it still like needs to balance, because sometimes, of course, the higher resolution, the better, but sometimes it's too fine, and it may magnify something that may not be that impacting. Oh, I'm sorry, I confused myself. Like it's so. But anyway, the 1 foot resolution is the highest one that we can acquire so far online, at least easily, freely. Yeah, but what was your question again? Sorry.
Yeah, I'm just wondering, do you have any challenges like for your study area to map the drainage networks?
Challenges, like for sure we recognize the limitations throughout the process, so that's why we have the validation process to kind of boost our confidence in the final results. So we chose to check the flow directions, which is also fundamental information that we can see very directly after we overlay the information of drainage onto the DM. So yeah, that's one strategy for us to consider the uncertainty or the challenges to cope with that. But yeah, like in terms of the challenges itself, that's a very good consideration. directions. And I don't know, like, how to answer the question other than what I've talked already. Yeah,
So maybe we have time for one more question from someone?
So thank you, really interesting talk and interesting work. I was wondering if there was any potential with this to be paired with kind of public health systems, specifically in like pathogen tracking, waterborne illness stuff. It seems like it could really interest in different areas.
yeah, that's really pressing. That's really an interesting point. I guess, yeah, for sure, our current scale probably don't have that much capacity, but that's the beauty of IoT. You can always embed other data sources onto the same platforms, virtual platforms, and to process the data. I guess we can, of course, some biosensors can be installed at along the waterway for some like spatial information, like data collections, and then can be embedded onto such IoT trunk pipelines, data pipeline, not drainage pipeline. Yeah, and I believe there are projects that has been already proposing or doing it. Yeah. And so far, like PC Swim also has a capability for water quality simulation, but it needs more data to support, which we don't really have. But still, we have the model or commercial or government models out there for this type of water quality simulations. So, yeah, so long as we figure out a way to make it automated or dynamic and get embedded to the IoT pipeline platforms. All right.
All right, good job.
Thank you.